Our tutorial project is about Apache Spark on Databricks Community Edition online. So the timeline of Apache Spark development was that it was developed in 2009 at UC Berkeley's AMP Lab. It was open sourced in 2010 under a BSD license. It was donated to Apache Spark or Apache Software Foundation in 2013 and has been a top contributed Apache project since 2014. Spark 1.0 came out in 2014. Project Tungsten, which we will cover, came out in 2015, and Spark 2.0 came out in 2016. So Apache Spark is a fast and general engine for big data analytics, processing with libraries for SQL, streaming, and advanced analytics. The Spark Core API features R, SQL, Python, Scala, and Java as programming functionality and has task scheduling. It is on resilience distributed datasets, which offers in-memory cache across the cluster for faster performance. For the higher level APIs, Spark SQL and data frames wraps coding infrastructure around regular SQL queries for more optimization. So this is an example of wrapping the SQL code around Spark SQL. For structured streaming, it combines streaming with batch and interactive queries for building end-to-end continuous applications. For machine learning libraries, it includes machine library algorithms, classification, regression, clustering, and dimensionality reduction. For GraphX, it's relatively new, but basically, if you can think of a social networking site with Twitter followers, it's basically each person is a node, and it figures out degrees of separation per node for an abstraction like Facebook friends or Twitter followers. And it's parallel computing for graph frames, which handles vertex degrees, such as PageRank as well. And you can import custom library packages to install on the Spark Core API by attaching them into the cluster. So for the cluster, the Databricks Online is one of the clusters that we will be using. It also features, you can also have Yarn as a cluster manager or as a standalone or Mesos. And Yarn stands for yet another resource negotiator from Hadoop, which we will not be covering. So Apache Spark is a unified analytics integration where you can integrate diverse environments, applications, and data sources. So here are the other things you can integrate it with. So for cloud computing on Databricks, you go to the Community Cloud website, you make a free account, and there's no computing fee. There's no computing fees for the free account. And then you can create a cluster and write a bunch of code. And the reason that we're using cloud computing is because it mitigates load time and frees up your local machine. And if you buy the subscription, you could purchase multiple clusters.
I'm going to show how to use Databricks. So first step is going to databricks.com. So this Databricks is a really nice platform that runs Apache Spark on top of the Amazon database. So if you want to try, on the right upper corner, there's a try Databricks button. And then you have two options. One is a full platform trial for 14 days free. And another option is a community edition for free forever. Yes, the difference is for full platform, it has unlimited clusters, and it's also able to schedule jobs, and it has BI tools. And the community edition is limited to 6 GB of memory in cluster, and it gives only one cluster. But it's sufficient to learn about Spark. running on Databricks. And approximate price of this premium version is when you run 4 clusters, it's about $240. But you can mix match GPU and CPU and RAM as much as you can. All right. So if you click, you're going to go with the community edition and then click start today. And then you have to provide your information and then sign up. Once you sign up, it'll direct you to this community cloud databricks.com. So this is the main page of the Databricks working area. And it has 3 featured notebooks. The notebook is the page that has that you can type the code. It has a interface of the Jupyter notebook. It's really similar to the Jupyter notebook. And these featured notebooks is really good examples to learn about Apache Spark that is running on Databricks. So introduction to Apache Spark on Databricks, and Databricks for data scientists, and introduction to structured streaming. These are really good examples that you can start from. And on the bottom, there's a function link that you can create notebook, job, cluster, and table and library. You can do the similar job from this task pane on the left side. And in the middle, there's a documentation link, and then recent file link, and then some news from the Databricks. So now I'm going to show you what functionalities, what features are there in this task pane. So click the workspace. There's the many links to documentation and release notes and training and tutorials and share data and users. And if you installed libraries, you can see the libraries that is installed. You can create folders and notebooks in your workspace. And recent tab shows all recent files. And data section, whenever you create tables or omnode files, you can see your data from this section. And then there's a cluster tab. You have to create a cluster, which is a cloud computing machine, in order to run notebooks. So let's go ahead and create a cluster here. You can name it whatever you like 1 test. And then you have to specify the version of the cluster. There are many Spark versions, but the latest one is 2.1. Normally the higher version is faster and nicer. And the native language of the Spark is Scala. So from different Scala languages, there are also different versions of the cluster. So by default, I always use Spark 2.1 and Scala version 2.1. And it creates 6 GB of cluster memory. And after idle of 2 hours, this cluster will be gone. And all the data in the memory will be gone. However, the notebook will be saved. Okay. There are multiple zones that you can choose based on your region. And then let's click cluster. So it's normally takes about 1 minute to run. So let's go ahead and explore other features on the task pane. So this under this job tab, if you scheduled any tasks, you can see all the tasks from here. And from the search tab, you can search your file in your directory. Yeah, and that's about it. And if you go back to the cluster, yes, the cluster is up and running. The thing that I always want to check is this library section information. I already installed one library called Avro, so it is installed, and it is automatically attaching whenever I create a cluster. All right, so this is about cluster. So let's go ahead and create a notebook. So under presentation, if you click this drop-down arrow, you can create notebook, library, or folder. Yes, let's create notebook first. So we can name as test. For each notebook, you can specify a default language. It could be Python, Scala, SQL, or R. However, you can change your language at any time for each cell. So, however, it would be nice to specify language that you want to use most. So, attach to this existing cluster, and then I'll create. All right. So this is how the notebook looks like. It has cell, and you can create another cell by pressing this button, and you can type any code since it is a Python notebook. So I could type like y equals range from 1 to 5, and it works, but it's not displaying anything. So print y. So this is how you use it. If you Control Enter, it runs only one cell. If you click Shift Enter, it runs the cell and then advance to the next cell. And if you want to use different language, you can just simply type $sign and then sh means shell, and you can type shell as a list. You can see the list in the directory. Or there's a Databricks file system command, always follows by %fs, and we can do the similar job here. And we can also use it's still running, I don't know why. Okay. We can also use SQL command, like select something, since we don't have a table. We can use SQL, or we can use R and type x equals random number 10 numbers. Probably going to print. Okay. So this is how we use the notebook cell. So you can run your cell by pressing this button also. You can run individual cell or all the above or all the below. And if you click this drop-down menu, hard to see. Okay, you can just copy cell and cut cell and then move around. You can do that. You can go up and down. You can also add a title for each cell. And you can do that. Okay. So, all right, let's move on to the next example. Now, we want to install a package. Before I want to run existing notebook, you have to attach this notebook to a running cluster. So just by simply just drop down and select a cluster, you can attach. So let's try import a library or a package called Scapy. And it gives error message because there's no library installed. So let's learn how to install library. So click workspace and then click this drop down arrow and then create and library. library source can be one of these three, Java or Python or Maven. So we want to install Python package. So you just simply just type the Python package name. What was that? Scapy. You can install this way, or if you have a downloaded compressed file for the library, you can drop down your library file here also. So let's do this. All right, it's really fast to install. Okay, so it's already installed, and then by clicking this checkbox, this library will be automatically attached to all clusters whenever you create another clusters. All right. All right. So if you run this import Scapy package, now it's working. So that's how you install packages. So let's learn how to upload data, since we cannot do anything without data. So go to the Data tab, and then click plus button to create a table, to upload a file, and to this cluster, and then you can upload file from your local location or any of these databases. So you need pre-existing credentials for these databases, but right now I'll just pick my file called population versus price.csv. So as soon as you drop the file, the file is uploaded, and then you have to keep this file location, because you have to use it later. All right. Okay. So all the uploaded files, before we go there, there's the option to clear all the outputs, existing outputs. So clear results. Then there's no output. Okay. So all the uploaded files will go to this location, file store tables. So if you run the list in the location, we can tell which one was the file that we uploaded exactly by this unique name. Yep. And yeah, we cannot tell, but just by pasting the path of the file that you uploaded here, this is SQL command. This is a Spark SQL command. It's when they deal about the data upload or reading, the syntax is slightly different than actual SQL language. So the uploaded file is loaded right now. I mean, the table is created using the uploaded file. And this is just an example that the Databricks has lots of example data set under this file. And this population versus price data I got is from this sample data as well. That's what I wanted to tell. And all right, so let's select all from the uploaded table. And this is the generic output of the fetching table. And the amazing thing about the Databricks is it has a built-in graphing tool. So if you click this, or actually, before we go that, whenever we have a data about state code like this, we can have a amazing matplot like this. So if you click the option, you can select different variables, and then you can plot the data on the map. this is kind of neat. And then this is an example using generating a table using schema. I'm using a different data set, data.csv here. Okay. Then we can also make a bar chart or scatter or whatever we want. And then this is an example of loading CSV file to the scalar variable. All right, and also make a bar chart. So there are many options to plot the data. So like scatter, line, area, pie chart, quantile, histogram, and box plot, QQ plot, and pivot plot. Yeah, this is a really nice tool for data scientists to examine the data, yeah, without like 20 lines of code. So this definitely saves time. And we can print schema, which is very important. I can print schema. And this is an example using R, reading data set. I'm opening diamonds.csv file. Yes, can make a line chart like that. Print schema is always important in this class. And this is lastly the Python example, how to import CSV file. And then I intentionally like make a plot for later use. Please bear with me. And this is the end of the loading CSV file using multiple languages. So one thing that you have to know is, even though you loaded CSV files from using multiple languages, it cannot be shared between languages because the data formats are different. So in order to share it between languages, you have to transform it. And that is out of scope of this demo. So we're not going to go for that. What else? We can do, it has a revision history option. So we can go back in time and see what code is better. Or if you want to restore it, just click this restore this revision, and that's it. And then, please don't restore. Okay, thank you. Okay. And then if you want to add any comments on any cell, just click this comment button, and then double click a cell that you want to add a comment. Why it's not working?
To highlight something.
All right, try again. It was working many times. All right. It's not working at this time. I don't know why, but that's how you do it. And then you can publish your notebook by click this publish button, and then you'll get a link. And then you can send to your manager or your colleagues. Then they'll have this published version of your notebook. And so you can copy this notebook, rename, move, delete, export. Export is kind of important feature. You can export to Databricks archive or source file or HTML format. So since this is using a SQL language as a default, if you export as a source file, it'll download .SQL file. If it was a Python, you'll see .py file. That's how you export. And import is going back to workspace and then import. And you can just drag and drop, I believe. The final demonstration is you can make a dashboard from your notebook out of this working notebook. And you can click any cell that you don't like. It deletes this cell only from this dashboard view. It's not deleting from the, you can make a title. You can drag and drop and move around this cell, which is nice. And then you can finalize by pressing this button, present dashboard. And this is how the dashboard looks like. And if the data was like connected to any streaming data, and if you hit update button, it'll update and then it'll change the plot.
Spark addresses today's challenges with CPU speed, end-to-end applications using one engine, and decision implementation based on real-time data. And there's a survey, and most of them prefer performance, advanced analytics, deployment, programming, and streaming. So challenge number one is hardware trends. As you can see, storage capacity and network increased by tenfold. However, CPU remained relatively the same. It's because we are close to the end of frequency scaling for CPU, where the speed cannot run more cycles per second without using more power and generating excessive heat. And to accommodate for CPU speed, hardware manufacturers have created multiple cores for parallel computing processing, which requires a form of MapReduce to compensate for distributed computation. And MapReduce is the transformation of nodes and records. And each node has a record, and where after each step has a synchronization step. And then reduce is the communication step between nodes in a cluster, or basically parallel computing, or just computing within a cluster. And the downfall of MapReduce is that the synchronization shuffle step has to wait until each node is finished for the next step to begin. So that produces higher latency if one node is slower than another, and because it has to finish completely before the next 4 nodes start computing in this example. So Spark's alternative to MapReduce is that first, instead of records, it uses column ranges. And with column ranges, it retains the schema level a model for indexing, which can be read inside the MapReduce record. It also uses DAGs, called directed acyclic graphs, which mitigates slow nodes by eliminating the synchronization step. So it just runs all the nodes at once with no synchronization and lowers latency. And it also supports in-memory data sharing across DAGs, so jobs can be done at very high speeds. In addition, Project Tungsten for Spark 2.0 mitigates runtime code generation, removes expensive iterator calls, views multiple operators, and it has a binary conversion system. And basically, the coder, the user, can write data frame code, which is in R, and it's relatively short. What Project Tungsten does is that it converts your R code, or whatever code that you wrote, into bytecode, in Java bytecode. And even though the length is relatively longer, the new conversion is a pointer arithmetic, which runs a lot faster because it's in bytecode. And then like the comparison between Spark 2.0 and Spark 1.6 is that it's a lot faster when processing rows per second. For the second demo, we talk about slightly CPU speed and ST parallel computing with word count, linear regression, and GraphX. So here's a speed comparison between MapReduce and Spark for logistic regression, key means, and PageRank. And as you can tell, Spark is 3 to 25 times faster than MapReduce. So for the second demo, I won't be running any of the the cells because of time. But basically, for parallel computing, this is a very simple example where A is 1, B is 2, C is 3, and you can write a data frame from that. Originally, it was a table, and then obviously the Spark has its built-in visualization tool, so you don't have to export the data. You can just view it in the Spark in the Spark engine. This is how you run code to find your data sets, as Mu Young mentioned. And then for parallel computing for word counts, we have a very simple example with 3 strings. It says, Spark, I am your father, may the Spark be with you, and Spark, I am your father again. And if you can imagine, if the strings were book size, or if the strings were multiple, like SMS messages or Twitter feed, it could be really long. And we use the parallel function in Spark so that the Spark version of MapReduce can parallel compute all this and figure out individually by node, how many times a certain word appears per string. So in this example, Spark appears the most with 3. This is a linear regression example with R. So, I could just run it real quickly, and then it appears on command, basically, because it's just that fast. You can't tell how fast it goes. And then for GraphX, it's relatively new. To visualize GraphX with like mutual friends and basically how to visualize nodes and degrees of separation. This is just like a stagnant view of GraphX when it comes down to seeing how nodes fit together in visualization. And then the last example is heat maps with the core being the hottest and the surrounding being the less hot when it comes down to the capabilities of running heavy visualizations in Spark. Back to the PowerPoint. So the second challenge is specialized engines. It's intuitive to think that you want to specialize an engine for special applications. However, with more than one engine, you have to install, configure, connect, and manage and debug everything. And performance dwindles because in the world of big data, you would rather move the computation to the big data than move the big data to the computation. So it's hard to dynamically allocate resources if you have more than one engine or more than one system. And oftentimes, you have to write temporary data files for another engine to process, and it slows down the process together. So that's the challenge. And to conquer that challenge, Spark uses end-to-end applications, and it's able to switch languages, like Mu Young showed us, implement specific libraries, and call on the same data set within the same notebook. And in addition, you can cache the data set in the RAM while implementing different computations. And the high-level APIs in the ecosystem allow for vertical integration, and performance gains are cumulative due to the aggregation of marginal gains in the Spark system. This is just graphs about the diversity in application solutions and methods. So number one would be business customer intelligence, would be the type of products built on Spark, and then data warehousing, and then streaming solutions. This is a graphic about how many components a product would use, and most of them would use 2 or more components. And then this is the trend of the diversity in the core Spark API and how many people uses which programming language. And this is the high-level APIs with data frame SQL, Spark SQL, and streaming. So this is the trend of just going up in general. So the third demo is the end-to-end application, and I will be showing you how to change, the languages, the changing languages to find the best models and applications, producing visualizations, Spark SQL, and JSON schema. In this graphic, basically the blue red, green, and purple goes into the same Spark bar chart. Basically, Spark has its own version of MapReduce, and the code comparison with lines of code condenses into a very small amount for Spark. Impala is another Apache system, and it's SQL. And Shark is Spark's predecessor to Spark SQL, and that's also very small in code as well. And Storm Streaming and Graph are streaming and GraphX respectively, and in totality, you really use little to very little code to do the same things in comparison to individual systems. So in the third demo, real quickly, if I can get there. So the third demo is end-to-end applications. And here is more Spark SQL code for running the Diamond dataset, as people are familiar from R. So you import it, and then you use SQL to make the table, which can be then converted into the actual graph. And this is fair good, the cut versus price and by color. And then you could use the Diamond dataset with R to produce the prediction model when it comes down to price and cut and color. And it does a really nice infographic, really nice visual. After that, you can separate by different cuts, and then you can do a log transformation so that they're all linear. So you could do better linear regression of the model for Diamond. And then, as shown before, this is how you use Spark SQL to implement a data set just on command, basically, and then you write the values in. And then after that, you use the capabilities of Spark to create the map of the United States as well as the globe, which is really nice. And then for PySpark, you can make a data set like this for a scatter plot, and then it's by grouping. So it looks like that. This is NumPy from Python, where you could do a scatter and then do a best fit model of a lambda function. This is specifically its sign, but basically it runs in the same notebook. And this is more QQ plots with PySpark. This is box plots with PySpark. And then over here is NumPy and matplotlib with Python. And this is a ggplot of prices of beef over the years. And then, so this is how you set up the data type within PySpark. So, string, integer, array, Boolean, double. And then you define a function. It's called JSON to data frame. And so, and then you use parallel in the Spark. So this is a JSON file. We covered this before. So basically, the JSON file looks like this, and then you display it, and it looks really, it's illegible for human eyes. What you do is you can print the schema, and it looks like this, and then you could set the keys and IDs. So in Python, you could write the exploded function to have keys and IDs for the certain values. And then to complete the schema, you write in this code, and then it produces a nice table, where then you could use the graph function to further your analysis for this JSON code. And then back to the PowerPoint, the third challenge is decisions based on data streaming. So streaming data may not be fully reliable because the node crashes. And when a node crashes, there's just latency lag, and there's artificial fluctuations in the graph because of the system, not because of the data. there could be asequential data where the data isn't coming in correctly in the right order or comes in late. And then there could be data inconsistency if multiple servers are storing the data stream. So the reason that we are concerned about data streaming is the relevance of news stories over time. For example, this is from Yahoo, and over the course of a day, different lines and colors represent the trends of different news stories and how popular they get. And and the way that Spark solves this is with structured streaming and node indexing. As covered before, Spark has a system that allows columns to be read within a node for indexing. And that fixes a lot of things. First, fault tolerances fixes node crashes. And then special filtering fixes the asequential data. Basically, you just add in a timestamp or special like indexing to make sure that it's coming in sequence. And then because of the index, it automatically fixes consistency. So what this does is for pure streaming, it's just input and output. Very simple. What Spark allows you to do is continuous application, which is the input of a stream and output of a sink is still there, but you can also add on ad hoc queries onto the stream data as well as static data. And then you can add in batch jobs onto that. So it's like three things into one. So basically, you use queries on top of streaming data, static data, and batch processes. And it allows the application to be very flexible in making real-time decisions. For real-time solutions from the cloud, you can personalize web results, automate stock trading, see trends in news events, prevent credit card fraud, and video and optimize video quality. So in this example, Convivia is a streaming service that has 4 billion streams per month, and it provides a lot of online streaming services. And what this does is, with the Spark nodes, each device that you stream the video is a decision maker, and the decision is in the code where it decides which server you want to stream your video from. So this really eliminates or mitigates streaming time, the buffer time needed. So that's example with data streaming. So the fourth demo with data streaming is I'll be covering streaming, library packages, and custom applications. This chart just shows how, because of the fully functional capabilities of Spark, it has more commits and lines of code, contributions, more than MapReduce, Yarn, HDFS, and Storm. So going back to the demo, so for the data streaming, this is just a mock data streaming, but this is how you would write the code to stream the data in. And then from there, it looks like this. From there, you can write more code to graph it. But basically, what this code does is it groups the streaming data per hour, and then you can use SQL to graph the code for opening and closing. So the close and open for streaming data can, replicate, stocks when, stock prices open and stock prices close. And then from here, you can use SQL to check if the number of opens is the same as the number of close. And the reason that we do that is to validate integrity. If we have, unequal numbers of open and closes, it might be less reliable. So right now, we have the same number of open and closes. So that's data integrity right there for making decisions on top of that. And then for the conclusion, the diversity of organizations, job field, and applications that use Spark will continue to grow as more people find use in its various implementations. So in a Spark survey, mostly it's data engineers and data scientists, but slowly there's architects, technical management, and academics. And then Spark will continue to dominate the analytical landscape with its efficient solutions to CPU usage, end-to-end applications, and data streaming. Right here is the slide where we went through a lot of tutorials to make this happen. And hopefully, I'll distribute the GitHub file